So let's look at another example. Sine t over 1 plus tangent t. So again, we're going to use the quotient rule. The derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. We saw that the derivative of tangent t was secant squared t, all over 1 plus tangent t squared. So if we express tangent in terms of sine and cosine, and express secant in terms of cosine, we can simplify things a little bit. Here's another example. We're going to need to use the product rule, and we have three factors, t, e to the t, and cotangent t. So we'll group two of them together and treat those as one factor, and then we'll have to apply the product rule again. So if we find the derivative of this, it's the derivative of the first factor times the second plus the first factor times the derivative of the second. And now we'll use the product rule again on this derivative. So it's the derivative of the first times the second plus the first factor times the derivative of the second. And then multiplying that through, I get e to the t times 1 plus t cotangent t minus t cosecant squared t. So we just factored out that e to the t. Here is an application problem. So an object with weight W is dragged along a horizontal plane by a force acting along a rope. So someone has pulling this rope and they're dragging this thing. If the rope makes an angle of theta with the plane, then the magnitude of the force is given by this equation. So this is a function of the angle theta, and m is a constant, the coefficient of friction. So it asks to find the rate of change of f with respect to theta. So we know that that's the derivative of f with respect to theta. So we use the quotient rule. So that numerator is just a constant. So the derivative of the numerator is 0 times the denominator minus the numerator times the derivative of the denominator. So that would be m cosine theta minus sine theta, all over the denominator squared. And then simplifying, this is what we have. The second part asks when is the rate of change equal to 0. So we simply set this equal to 0 and solve for theta. So this is only going to be 0 when the numerator is 0. So all we need to worry about is setting that numerator equal to 0. So I will cancel the w's, and I can cancel one m factor. And if I bring this cosine theta term over here to the other side, and theta equals m, then taking the inverse tangent or the arctangent of m. So theta is, the rate of change is 0 when theta is equal to the arctangent of the coefficient of friction, m. So part C is if W is 50 pounds and that coefficient of friction is 0.6, draw the graph of f as a function of theta and use it to locate the value of theta for which df d theta is 0. So we know that df d theta is 0 where that function has a maximum or a minimum. So we graph this function with w and m given to us in the right places. So that's this red graph. And then the local minimum occurs somewhere around here. And I've also graphed this derivative. And you can see where the derivative crosses at 0.504 approximately. And that just happens to be the arctangent of 0.6. So this confirms our answer from part B. When the coefficient of friction is 0.6, that's when the rate of change of the force is 0. And here's just another example of that. You can see that the function graphed what the value of arctangent 0.6 is.